Welcome back to the deep dive. I have to be honest with you right off the bat. I think we're gonna maybe ruin something for you today.
Oh,
Or, well, ruin is probably the wrong word. Let's say we're gonna fundamentally shift your perspective on the world.
okay, I'm intrigued.
Specifically, we're gonna change the way you look at a tea kettle.
A tea kettle, that's a
Yeah?
that's a very domestic place to start for a deep dive on energy infrastructure.
It is, isn't it? But just hear me out. I've been buried in this stack of research you sent over all week. Articles on advanced nuclear physics, diagrams of steam mechanics, the history of the electrical grid, the whole nine yards.
Hmm.
And I had this moment of total, utter disbelief. I'm calling it the grand irony of human technology.
It is a bit of a shock when you first realize it, isn't it?
It's a huge shock.
We tend to view our energy grid as this futuristic, pulsating beast of high technology.
Exactly. I mean, think about the context here. We are living in the 21st century. We have split the atom. We have peered into black holes at the very edge of the observable universe.
We simulate quantum weirdness on supercomputers that basically fit in our pockets.
Yes, we are, by all accounts, a sci-fi civilization. But then you dig into how we actually keep the lights on, specifically looking at nuclear power, which is supposed to be the absolute poster child for high tech. And what do you find at the bottom of it all?
You find the 19th century staring right back at you.
You find a tea kettle, a glorified, radioactive, terrifyingly expensive tea kettle. I couldn't believe it. I was reading through this breakdown of nuclear plants, and the core premise is we use the most advanced, dangerous, and complex physics known to man. Just to boil water.
That is the aha moment right there. It feels incredibly anticlimactic.
It does.
You expect, I don't know, antimatter containment fields or direct energy extraction from the quantum phone. But no. The vast majority of global power generation, and we aren't just talking nuclear here, we're talking coal, gas, biomass, even some forms of solar. It all boils down quite literally to boiling water.
So that's the mission for this deep dive. We really need to unpack this disconnect. I want to understand why, despite all our genius, we are effectively still using technology that James Watt would recognize from the 1700s.
Right.
Is it laziness? Is it a lack of imagination? Or is there something else going on? And then I want to get to the stuff in the back half of the notes, the elegant outliers, as you called them, the technologies like solar panels and these wild nuclear diamond batteries that actually managed to skip the steam phase entirely.
Yeah, the exceptions that prove the rule.
Exactly. But let's start with the shock. You're the expert here. Just validate this for me. Are we really just burning rocks to spin a fan?
In essence, yes. But to be fair to the engineers, it's a very, very sophisticated fan.
I'm sure it is.
Yeah.
But the premise remains.
No, I get it. It feels like a cheat. To really appreciate the irony, though, you have to look at the anatomy of a nuclear power plant.
Okay.
Because a nuclear plant isn't really one machine. It's two very different technologies from two completely different eras just smashed together.
Right.
You have the high-tech side, and then you have the low-tech side.
Okay, let's break that down. Part one, the reactor. This is the sci-fi stuff. This is the part that requires PhDs at security clearance to even understand.
All right. Inside that reactor vessel, we are doing something truly incredible. We are harnessing the strong nuclear force.
The force that literally holds the universe together.
The very same. We are taking uranium atoms, specifically uranium-235, and we are slamming them with neutrons moving at incredibly high speeds.
This is fission. And just so we're clear on the mechanism, because I think people hear fission and just think explosion, what is physically happening to that atom?
Okay, so imagine the nucleus of an atom, like a tightly packed ball of marbles. It's held together by immense tension.
Right.
When we fire a neutron at it, it's like throwing one last marble into a ball that's already under way too much pressure. The whole thing just becomes unstable and shatters.
It split.
It splits into two smaller atoms. We call them fission products. And in that process, a tiny fraction of its mass is converted directly into energy.
This is Einstein's equation in action, right?
Exactly.
Yeah.
Mass turns into energy.
Yeah.
And because the c in that equation is the speed of light squared, which is a gigantic number,
A tiny bit of mass.
creates a massive amount of energy.
Yeah.
Plus, the split itself releases more neutrons, which then go on to hit other uranium atoms, creating a chain reaction.
A self-sustaining reaction.
It is physics at its most extreme. We are manipulating matter at the subatomic level.
Okay, so we have this cathedral of high-end physics. We have control rods, we have moderators, we have supercomputers running calculations to keep this chain reaction stable and not,
Go boom.
Right. And the output of all that complex, dangerous, brilliant physics is what?
Thermal energy. Heat. Just massive, intense, blinding amounts of heat.
And that's it. That's the high-tech part done. We use
Yeah.
the secrets of the cosmos to create a very hot fire.
Precisely. And that brings us to part 2, the conversion. This is where we step out of the quantum realm and walk straight back into the Victorian era. Because we have all this heat. But heat isn't electricity. You can't charge your iPhone with heat. You need electrons moving through a wire. So how do we bridge that gap?
This is the low-tech disconnect.
We use the heat to boil water. We take that thermal energy, we transfer to a fluid loop, and we turn water into high-pressure steam.
And then we shoot that steam through a turbine.
Which, let's be honest, it's just a very fancy windmill.
Right?
The steam hits the blades, the turbine spins at incredible speeds, and that spinning motion turns a generator.
And a generator is just magnets rotating inside a coil of wire.
That's all it is. That rotation pushes the electrons. It creates electricity the exact same way a hand-cranked radio does, or a bicycle dynamo light.
Just on a gigawatt scale.
Just on a massive scale.
That is the takeaway that just blew my mind. We have mastered the fundamental forces of the universe, but our best method for harvesting that power is still just a fancy way to turn a crank. It feels, I don't know, almost insulting to the uranium.
It does feel a bit undignified for the atom, doesn't it? I'll hold the secrets of the cosmos, I am the destroyer of worlds, and you're using me to make steam.
Exactly. It begs the question, is this just laziness? I mean, are the engineers just phoning it in? Is this a case of, if it ain't broke, don't fix it? Or is there a genuine physical reason why we are still addicted to steam?
Right.
Because if I were an alien looking down at Earth, I'd think, wow, these guys really, really love boiling water.
That is the million-dollar question. And I can assure you it is not laziness.
Okay.
Engineers would love nothing more than to get rid of all the plumbing. Steam is dangerous. It's corrosive. It's under incredibly high pressure. If a pipe bursts, people can die.
It's a huge weak point.
A huge one. We don't use it because we lack imagination. We use it because of physics and pragmatism.
Yeah.
Specifically, what you could call the magic of water.
The magic of water. Okay, let's unpack this. Why is water so special? I drink it, I swim in it, but I don't usually think of it as some engineering marvel. Why not use something else? Why not heat up, I don't know, nitrogen or mercury?
In the world of thermodynamics, water is a total superstar. It has a few properties that make it almost impossible to beat for this kind of power generation.
Okay.
The first and most important one for the turbine is expansion. When water turns from a liquid to a gas to steam, it doesn't just change its shape, it changes its volume.
Right.
Drastically.
How much are we talking? Give me a visual.
It expands about 1,600 times in volume.
Whoa. Wait, 1,600 times?
Yes. So imagine a single cardboard box filled with liquid water. Now imagine you heat it up, and instantly that water wants to occupy 1,600 boxes worth of space.
Okay, wow.
If that happens in an open field, it's just a cloud. But if that happens inside a confined reinforced steel pipe,
That creates incredible pressure.
immense pressure. It's basically a controlled explosion, yes. That pressure is what we use to drive those huge turbine blades. You need that violent expansion to get the mechanical work done. If you just used hot air, you wouldn't get that same phase change kick.
So it's not just that it gets hot, it's that it gets big. And fast. Yeah.
Exactly. It pushes hard. And then there's a second factor, which is arguably even more important, especially for nuclear power, heat capacity.
This is the safety angle, right?
This is the safety angle. A nuclear core is incredibly hot. We're talking hundreds of degrees Celsius, and the fuel pellets themselves get way, way hotter.
And if you don't remove that heat,
The fuel melts. That's a meltdown.
Yep.
Water has a very high specific heat capacity.
Yeah.
It is incredibly good at absorbing thermal energy and carrying it away. It's like a sponge for heat.
So it serves a dual purpose.
It does. It spins the turbine to make the power, but it also keeps the reactor from destroying itself.
So it's the fuel for the engine and the coolant for the engine at the exact same time.
Precisely. And then there's the third factor, which is the most pragmatic one of all.
Let me guess. It's cheap.
It's practically free. It's everywhere. It's abundant. If we use some exotic fluid, and some advanced reactors do, like liquid sodium. Why? Liquid sodium is toxic, it explodes if it touches air, and it's very expensive. Water is safe, we know exactly how it behaves, And if it leaks, it's usually just wet.
Well, radioactive wet in this case, I guess.
True, inside that primary loop, it's radioactive.
Yeah.
But the physics of the fluid itself are completely understood.
So the argument for steam is basically that it works and it's efficient.
It is surprisingly efficient. We tend to look down on old tech, but modern steam turbines, especially in what we call combined cycle plants, are absolute masterpieces of engineering.
Really?
Oh, yeah. They are incredibly good at converting that heat into motion. We're talking 40, 50, sometimes even 60% efficiency in converting thermal energy into electricity.
That doesn't sound that high.
It might not sound high to a layperson who wants 100%, but in the world of thermodynamics, that is fighting for every single inch against entropy.
Okay.
We have spent 300 years refining the steam turbine. The tolerances on those blades are tighter than a Swiss watch.
That's the pragmatism part. We have centuries of data on how to build a better kettle. So why reinvent the wheel when the turbine works so well?
Precisely. And to show you just how deep this addiction to steam goes, we have to talk about the future. You mentioned fusion earlier.
Oh, yes. The holy grail, the artificial sun, ITER. This is supposed to be the technology that saves us all, right? Unlimited clean energy, smashing hydrogen atoms together like the sun does. Surely fusion doesn't use a steam turbine.
I hate to be the bearer of bad news.
No, don't tell me. Please don't tell me.
Even with fusion, the most advanced futuristic technology we can possibly dream of, the current plan for reactors like ITER is to use the intense heat generated by the plasma
To boil water?
to heat cooling loops, which then generate steam and then spin a turbine.
That is, honestly, that's hilarious. It's kind of depressing, but it's also hilarious.
It really is.
So even if we build a literal star in a jar suspended by magnetic fields at millions of degrees, we're just using it to make a really, really expensive cup of tea.
We are just building a hotter fire. We can't escape the steam engine. The method of creating the heat changes. Wood, coal, gas, uranium, hydrogen, plasma. But the method of catching the energy, it's almost always steam.
So is that it? Are we doomed to be steampunks forever? Is there no technology that escapes the boiling water gang? Because the notes you sent had that section, the elegant outliers.
There is hope. There absolutely are technologies that skip the steam phase entirely. And the most prominent one is something you probably see every day. Solar photovoltaics, or PV.
Solar panels. Now, this is interesting because the notes describe solar PV as the pure science alternative. It's like the rebellion against the steam engine.
It really is. Think about the sensory experience of it. If you stand next to a coal plant or a nuclear plant, you hear things.
Oh,
You
yeah.
hear the hum of the generator, the hiss of steam valves, the whir of pumps, maybe the grinding of coal crushers. It's a mechanical beast. It breathes. It's alive.
It's visceral.
Right. Now, stand next to a solar panel out in the middle of a desert. What do you hear?
Nothing. Silence.
Absolute silence. Because there are no moving parts. There are no fluids. There is no steam. It is a solid-state device. It is effectively a quantum trap.
I love that phrase, quantum trap, but how does it work? If we aren't boiling water to spin a magnet, how do we get the electrons to move? Because my understanding of electricity is at some point, you have to push the electrons.
We do push them, but we don't use a magnet to do it. We just cut out the middleman.
Okay.
In a nuclear plant, the chain is nuclear energy to thermal energy, which turns to mechanical energy, which finally turns to electrical energy.
Right.
It's a long, lossy chain.
Right, with waste at every step.
Exactly. In a solar panel, we use the photoelectric effect.
Which got Einstein his Nobel Prize, if I recall correctly. Everyone thinks it was for relativity, but it was this stuff.
Correct. And the mechanism is just beautiful in its simplicity. You have a semiconductor, usually silicon. Now, silicon is unique. It forms a crystal lattice. We treat it, we dope it with other chemicals to create a permanent electric field inside the crystal. It's like a coiled spring just sitting there waiting to be sprung.
A silicon sandwich.
A silicon sandwich with an electric potential built right in. When a particle of light, a photon, flies down from the sun and it hits that silicon,
Yeah.
it crashes into an atom. And if it hits with enough energy, it physically knocks an electron loose from its orbit.
That's like a billiard ball hitting another ball.
That is a perfect analogy. The photon hits, the energy transfers to the electron, and the electron gets excited and jumps up. Now, normally that electron would just fall back down into place.
But
because of that electric field we built into the sandwich, that loose electron is pushed in a specific direction. It flows.
And flowing electrons are electricity.
Direct conversion. One step. Light hits rock, rock makes power. No cranks, no pistons, no steam. It just happens. Silently at the atomic level.
That does sound superior. I mean, purely from a cool factor perspective, solar wins, hands down.
Oh, for sure.
Harvesting energy directly from a star without needing any 1800s machinery,
Hmm.
that's the dream. It feels cleaner, not just environmentally, but conceptually cleaner.
It is the dream. It's elegant. But and in engineering, there is always a but.
The boiling water gang strikes back.
They do. Because even within the world of solar, there is a traitor. Have you ever heard of concentrated solar power, or a CSP?
Is that the one with all the mirrors? I've seen pictures of these. It looks like a sci-fi cult gathering in the desert.
Yes. Picture a massive field with thousands of mirrors, all controlled by computers to angle and reflect the sunlight at a single point on top of a central tower.
Right. It looks like a death ray.
It looks incredibly futuristic.
Yeah.
And what happens at the top of that tower?
What happened?
The light is so concentrated that it gets incredibly hot, molten salt hot.
Ah.
And they use that heat
Oh.
to boil water.
You're kidding me. Even the sun can't save us from steam.
Even in solar, steam tries to creep back in. Because, again, steam is an efficient way to move energy around. And more importantly, heat is easier to store than electricity. You can keep a tank of molten salt hot for hours after the sun goes down, so you can keep boiling water at midnight.
I see. So that's the advantage. Batteries for solar panels are still expensive. A giant tank of hot salt is, well, it's just a tank.
Exactly. But if we stick to the pure photovoltaic panels, the ones on your roof, we have a true battle of philosophies. The steam engine versus the quantum trap.
So why doesn't solar just win? If it's so elegant, if it has no moving parts to break, why are we still building nuclear plants and gas turbines? Why isn't everything covered in silicon?
It comes down to two things, really. Density and demand. And this is where the old school tea kettle really shines.
Let's talk density. There is a comparison in the notes that I love, the gummy bear comparison.
Yes, this is the ultimate trump card of nuclear power.
Yeah.
A single pellet of nuclear fuel uranium dioxide is about the size of a gummy bear. Just a tiny little black cylinder.
Okay.
That one pellet contains as much energy as 1 ton of coal.
One gummy bear equals 1 ton of coal. That is staggering.
It is mind-boggling. To get that same amount of power from solar, you would need acres and acres of land covered in panels.
Right.
Nuclear is incredibly energy dense. You can generate gigawatts of power enough for a whole city from a relatively small footprint.
Yeah.
Solar is diffuse. The energy is spread out over the whole surface of the Earth, so you have to catch it with really big nets.
So if you need massive power for a city like Tokyo or New York or for a heavy industrial factory, you can't just slap some panels on the roof. You need that density. The boiling water method is still the king of density.
Exactly. And then there is the on-demand problem.
The sun goes down.
The sun goes down. And unfortunately, human beings have this habit of turning on their air conditioners and their TVs and their ovens right around 8 p.m. when the sun is long gone.
Right when power demand spikes.
We cannot command the sun to shine, but we can command a steam turbine to spin. We can boil water day or night, rain or shine.
So until we have massive, cheap batteries to store all that solar power from the day, the tea kettle keeps its job.
Correct. The tea kettle provides what we call the base load, the reliable, steady power that holds the entire grid up. Solar provides the peak power when the sun is out. They actually work well together, but they're fundamentally different beasts.
Now, you mentioned there are other non-steam contenders, wind, for example.
Wind is interesting. It does skip the steam, but it's still mechanical. It's just harvesting kinetic energy directly. The wind hits the blade spins the generator.
So it's basically just the turbine part of the power plant?
But nature provides the push instead of steam.
And hydropower?
Same thing. Gravity pulls water down a hill, the water hits a turbine, the turbine spins. No boiling, but still moving parts. Still mechanical.
So really, solar PV is the only major one that has no moving parts, no mechanical action at all.
It was.
Yeah.
Until we started looking at the ultimate sci-fi technology.
Okay.
The nuclear diamond battery.
This is the part of the research that I really wanted to get to. This sounds like something out of a comic book. Nuclear diamond batteries. It sounds fake. It sounds like snake oil.
It sounds totally made up, I agree. But I promise you, the physics are solid. This is the revenge of pure science against the steam engine.
Okay.
It's a battery that runs on nuclear waste, lasts for thousands of years, and has 0 moving parts.
So it's nuclear power, but without the steam, without the turbine.
Correct. It is effectively a nuclear solar panel.
Okay, you have to break this down for me. How does it work? Because I'm picturing a diamond with a tiny little nuclear reactor inside it.
It uses a concept called beta voltaics. Remember how solar panels work? Photons from the sun hit silicon, they knock electrons loose, and that creates a current.
Right. The billiard ball effect.
In a nuclear diamond battery, we don't use photons from the sun. We use beta particles
And where do we get beta particles?
from the trash. We take radioactive graphite blocks from old, decommissioned nuclear reactors.
Okay.
In the early days of nuclear power, specifically with gas-cooled reactors, they used tons and tons of graphite to moderate the reaction. Over time, that graphite got bombarded with radiation, and it became radioactive itself. It's full of carbon-14.
Carbon-14. That's the stuff we use for carbon dating, right? To see how old things are.
The very same.
Right.
It's a radioactive isotope of carbon. And as it decays, it naturally shoots out high-energy electrons. This is what we call beta particles.
So the waste is just spitting out energy. It's bleeding energy.
Constantly.
Yeah.
For thousands and thousands of years. So here is the genius part. We take that radioactive graphite, we purify it, and we use a process called chemical vapor deposition to turn that radioactive carbon into a diamond.
Wait, you turn the waste into the diamond?
Yes. Or, in some designs, you encase the waste inside a lab-grown diamond. Diamond is just carbon, after all. A very specific arrangement of it.
Why diamond? Is it just to make it look fancy? Or to charge more money?
No, it's because diamond is what we call a wide bandgap semiconductor. It works just like silicon, but it is much, much stronger and more durable.
I see.
When those high-speed beta particles from the decaying waste smash into the diamond's crystal lattice, they do exactly what the photons do in a solar panel. They knock electrons loose.
And that creates the current.
That creates the current. But here is the critical difference. A solar panel needs the sun to shine on it. It stops working at night.
Right.
A nuclear diamond battery has the sun trapped inside it. The radioactive waste is the power source, and it is shooting out particles 247.
That is wild. You've basically bottled a star, but instead of fusion, it's decay.
Yeah.
We're harvesting the slow death of the atom.
It's a very poetic way to put it.
Yeah.
And because the half-life of carbon-14 is so long, this battery doesn't just run for a day or a week.
How long are we talking?
A carbon-14 diamond battery could theoretically produce power for 28,000 years.
28,000 years. That's not a real number. That's longer than human civilization has existed.
It's effectively an eternal battery.
Wow.
It's indestructible. It uses dangerous nuclear waste as fuel, so it actually helps clean up the planet, and it runs forever.
Okay, I'm sold. Where can I buy one? Why isn't my phone running on this right now? Why aren't we driving cars powered by diamonds? Because this sounds way too good to be true.
Now we get to the cons. The reality check.
There's always a catch. I knew it.
The catch is power density. We talked about how energy-dense nuclear fuel is for a reactor. Well, beta voltaics are the complete opposite. While it lasts forever, it produces energy very, very slowly. It's a trickle charge.
So I can't run a Tesla on it.
Not even close. You couldn't even run a smartphone on one unless you had a battery the size of the phone itself, or a massive stack of them.
Oh.
It isn't a fire hose of energy like a steam turbine. It's a tiny, steady drip.
So what is it good for? If I can't scroll Instagram with it, why do we care?
It is perfect for things that use very little power, but that you never, ever want to have to replace. Think about a pacemaker.
Oh, wow. Yeah. You don't want to have open heart surgery every 10 years just to change a battery.
Exactly. Imagine a pacemaker that outlives the patient by thousands of years. Or think about deep space sensors on a probe heading to Pluto. You can't change the batteries out there, and solar is way too weak that far from the sun.
Or hearing aids.
Hearing aids, sensors embedded in the concrete of a bridge to monitor structural integrity for centuries. Devices that need a low, steady hum of electricity for decades or centuries. That is the sweet spot.
No, it's still incredible, though. It feels like the first step towards something completely new. Like we're finally figuring out how to use the atom without the steam engine.
It is. And there are huge manufacturing challenges, of course. Making lab-grown diamonds that are perfect enough to capture all that radiation without degrading over millennia is extremely difficult. And then there is the marketing nightmare.
The marketing nightmare, what's that?
Try convincing the average person to put a nuclear battery in their pocket.
Right.
Or in their chest.
Hey, would you like to buy this radioactive diamond for your heart?
It's perfectly safe. The diamond shields all the radiation. And its true diamond is one of the hardest radiation shields in existence. Nothing gets out. You could sleep with it under your pillow and get less radiation than you do from eating a banana.
But the word nuclear just scares people.
It's a huge psychological hurdle. We have a hard enough time convincing people to live near a steam-based nuclear plant, let alone put a tiny one in their ear.
That's a very fair point.
But the concept stands. It proves that we can generate electricity from nuclear sources without boiling water. It is physically possible.
Before we wrap up, the notes mentioned one other non-steam nuclear tech, something called an RTG.
Yes, the radioisotope thermoelectric generator. It's worth a brief mention because it's sort of the rugged older brother of the diamond battery. It's been around for decades.
Is this what's on the Mars rover?
Yes. Curiosity and Perseverance, the rovers on Mars, they don't use solar panels because the big dust storms can cover them up and kill the robot.
So they use these RTGs.
They do. It's basically a lump of plutonium-238.
Plutonium, okay, that's the heavy stuff.
It is. And it decays so aggressively that the lump of metal just gets red hot. It actually glows.
Okay, so it's hot. Do they use the heat to boil water? Please tell me they don't.
No. That's the cool part. They use something called thermocouples. It's a special material that creates electricity when one side is hot and the other side is cold. It's called the Seebeck effect.
Oh, no moving part.
No moving parts at all. It just sits there, glowing red hot, and the temperature difference between the plutonium and the cold of space dries the electrons.
So it is possible. We have the tech, diamond batteries, RTGs, solar PV. The elegant outliers do exist.
They do.
Yeah.
But they are niche. They are for space, for low-power devices, or for when the sun is shining brightly, for the heavy lifting, for the grid, for the factories that build the cars and the smelters that make the steel. We are still stuck with the steam engine.
So let's bring this all back to the grand irony we started with. We've gone from the massive scale of nuclear steam engines to the atomic elegance of solar and these diamond batteries.
And the pattern is pretty clear. Incremental progress builds empires. We figured out a way to boil water in the 1700s, and instead of abandoning it for something cooler or more sci-fi, we just perfected it. We made it bigger, hotter, higher pressure, and more efficient.
Yeah.
That's what our civilization is built on. The boring but effective tech.
While the cool but difficult, the solid state, the quantum stuff is tantalizing. It points to the future. It hints at a world where we don't need all the plumbing anymore.
It does. It reminds us that there's always another way. We are capable of dreaming up antimatter drives and eternal batteries, but we're also pragmatic enough to stick with what gets the job done today.
It's a balance, then. We are cavemen with bitter fire, but we are reaching for the stars.
That's a beautiful way to put it. We use the fire to build the ladder.
So the next time you go to the kitchen to make a cup of tea and you hear that kettle start to whistle,
remember that you are holding a tiny, tiny version of a nuclear power plant in your hand.
Or rather, the nuclear power plant is just a giant, really complicated version of your kettle.
Touché.
Keep looking at the world differently. Question the machinery behind the magic. We'll see you in the next deep dive.
Goodbye, everyone.